Section 1.7, Introduction to Proofs. Some terminology to get out of the way. A theorem is a statement that can be shown to be true. So what we're going to be doing in this section is making theorems and then using proofs to show that they are true. A proof is a valid argument that establishes the truth of a theorem. To do so, it has a couple tools that we'll be using. So we can use axioms or postulates. These are kind of super basic statements that it's hard to argue they're not true, right? They're kind of taken at face value. This is something like A is equal to A, or a line can go on forever, right? They're kind of building blocks that are too basic to break down any farther. Premises, we've already seen how this works in previous chapters. So this is given pieces of information, right? It might be a definition, or it might be a starting point, a starting assumption. And then finally, we can use previously proven theorems, because that's how we further, get further in these things, is that we have building blocks we've already proven and we make them bigger and bigger and bigger as we go. Theorems are sometimes called propositions, lemmas, or corollaries. These are just kind of like loose translations you can have on them. A proposition tends to be a less important theorem, right? We tend to call something a theorem when it's a really big deal in a postulate otherwise. Lemmas are smaller theorems proven along the way. So if we have a really deep, meaningful mathematical theorem and we're writing a paper, we actually might have to prove, right, step 3 up there, previously proven theorems. We would call those previously proven theorems lemmas if they were new building blocks we were creating along the way. And the final corollaries usually happen after the big theorem, right? They're the fallout. They're other big takeaways we can get that are given sort of for free after we've proven the theorem. So we're going to learn 3 basic techniques here: direct proofs, proof by contraposition, and proof by contradiction. Let's start with the direct proof. Now, this section can be difficult. What I'm going to ask you to do is to lean into the idea that we're living in our own little world here that we've created. And by that, I mean just use the knowledge that we've had in class so far. So one of the things we're going to be using pretty often, because we're wanting to start with some really basic proofs, is odd and even integers. So in this green box here, I have an integer n is even if there's an integer k such that n is equal to 2k, and odd if there's an integer k such that n is equal to 2k plus 1. Don't bring in a lot of outside knowledge. All of you have obviously been dealing with odd and even numbers for a very long time, and so you might want to do something like, hey, this is divisible by 2. No division in here. Let's stick directly to using this definition as given. So we kind of want to stay in the realm of information we've gained in class so far. It's going to kind of keep us safe in our little sandbox here, and you should lean into that. So act like, for this chapter, I'm probably going to repeat this several times, but this is your entire universe of knowledge about even and odd numbers. These are totally new definitions until today. You've never heard of an even or an odd number, and I'm telling you what they are. So we're going to stash this right up here at the top, because we're going to be using it for a couple things. And now finally, what is a direct proof? Well, a direct proof of P implies Q is going to make the assumption that P is true, and then use rules of inference, which we've been working on all the previous chapters, axioms, and logical equivalencies to show that Q must be true, right? It's going to construct that valid logic to show Q must also hold true. So let's see an example here. The product of 2 odd numbers is odd. Let m and n be 2 odd integers, right? We're going to do this directly. So we're going to start with the assumption, right? If they are 2 odd numbers, let's show their product is odd. So direct proof. So we've gotten started here. This is our assumption. This is going to be our premise, as it were. So now, where do we go from here? Well, that green box up there. What do we know about being odd? If you're odd, by definition, that means there's 2 integers. Don't be thrown off by me using k again. You could use whatever integer, letter, you can use whatever letter you want to represent this integer. It's a variable. Don't get caught up in the fact that the definition up there has a k, right? The k could be anything. It's just giving it a name to reference it, right? It's instantiating it. So I have two integers, k1 and k2, such that m is 2k1 plus 1 and n is 2k2 plus 1, right? Because they're both odd, and this is what it means to be odd by definition. Well, now I can go back and look at what happens when I multiply them. So I have mn and I get this multiplication. Now keep in mind what the goal here is. We're trying to show that it's odd. And the only thing we know about odd numbers is this definition right here. So I got to get back around to that. If you want to show that m times n is odd, you need to make it look like 2 times an integer plus 1. So I just do some algebra. And here's where the magic happens, right? I've maneuvered it into 2 times the following stuff plus 1. Well, that stuff in the middle is just an integer. So now look at the form m times n has taken. It's 2 times an integer plus 1. And we know what to call that. We call that odd. So I've started with the assumption that m and n are odd, and I've shown that that directly implies mn is odd. Direct proof, P implies Q. Let's try another. The sum of two even integers is even. It's a direct proof. So we're going to start with the assumption, let m and n be two even integers. Well, by definition, again, I'm going to apply the definition. What does it mean to be even? There exist integers k1 and k2, such that m is 2k1 and n is 2k2. Let me stop right here. Well, in chapter 2, we're going to be going into set notation a lot more, but I want to go ahead and introduce it here so we can start using it to just make these even more compact so you can get a feel for what this is going to look like. One way to state there exist a k1 and k2 that are integers such that I could state it like this. Then there exist k1 and k2 that are members of the set of integers. Remember, we've seen that z before. So this says k1 and k2 exist and they are integers such that, and then the rest follows, m equal to k1, n equal to k2. So now I'll go back and look at the addition. M plus n then could be rewritten as 2k1 plus 2k2. Factor out the 2. Now I have m plus n in the form of an even integer. So I've shown you that mn is even. And this completes the proof. Let's move on to proof by contraposition. This one is a little bit trickier and is going to feel wrong, right? If you're following the logic behind it, I think everyone has this experience at some point, right? You're going to witness me do this and you're going to think, oh, you know, I get it or whatever, but then you're going to start to do the homework. And at some point, this is going to start to feel like you're not even showing what you want to be showing. So this one you're going to lean into the idea that the contraposition is logically equivalent to the implication. So a proof by contraposition wants to show P implies Q, but for various reasons that might be really hard to do. We'll see why in a second. So instead it makes the assumption that not Q is true and uses the same tools as before to show that not P is true. Okay, so let's see an example. If m and n are integers and m times n is even, then m is even or n is even. So let's try to do this directly, because that would be my go-to. Let m times n be an even integer, then there exists a k such that m times n is 2k. Right? I'm just applying the definition. But where do you go from there? if we're going to flow from m times n and now into the 2k, there's not really any algebra I can do with 2k. There's no way to break that down farther. There's no way to even get the m and the n alone without doing, you know, if you sit down and start tinkering with this, you'll get a bunch of fractions, and that doesn't even leave them being integers. So let's analyze this a little further. What I was trying to do is I was trying to take m and n was an even integer and use that to directly show that m is even or n is even. So I was trying to take this p and use it to directly imply that q or r. So what would the contraposition do in this case? Well, the contraposition of p implies q or r would be not q or r implies not p. That's equivalent to go ahead and De Morgan's that negation into there. Not q and not r then should imply not p. So what I want to show in this case then, to complete my proof, is I want to show if m is odd, right, that's the not q, and if not r, that's n is odd, then mn is odd. And this, as we're going to see, is actually a lot easier to show. So even though it's a little more convoluted path to get there, the contraposition is going to be an easier proof. Note the negation there gives me the if-then statement. So now we're going to start with the assumption that both m and n are odd. Remember, we're just using this definition. Well, if they're both odd, that suggests there exist two integers, where m can be written as 2k1 plus 1, and n can be written as 2k2 plus 1. So we give those two integers names so we can apply the definition. Now we look at the multiplication of m and n. Can we write it, the product of that multiplication, as an odd number? Sure enough, we can. We get 2 times an integer plus 1, so m times n has the format of an odd integer. So we can conclude, therefore, mn is odd. So we've shown that the contraposition holds true, which we know from seeing the truth table, and we also use logical equivalencies to show that that's equivalent to showing that p implies q. Let's try another. If n is an integer and 3n plus 2 is even, then n is even. So contraposition, we're going to reverse the direction of the implication and negate. So we will be starting with the assumption that n is odd. Apply the definition. If n is odd number, by definition, there exists an integer, call it k, such that n is equal to 2k plus 1. So now I can substitute for that n the 2k plus 1. Do some algebraic manipulation, and I get that I can write 3n plus 2 as 2 times an integer plus 1. Thus, 3n plus 2 is odd, and we've done another proof by contraposition. Final technique, proof by contradiction. A proof by contradiction of P assumes that not P is true and uses rules of inference, axioms, and logical equivalencies to derive a contradiction. So suppose there are an infinite number of prime numbers, right? Let's take a different approach here. Let's leave the odd and even behind us. Let's take an entirely different type of subject matter here. So let's say there's a finite number of prime numbers. It can be really hard to decide how to start a proof like this. So what we need to do is think, okay, what does it mean to have a finite number of them? Well, if there's a finite number of them, it means I can put them in a list. And that list is going to have an endpoint. Note that it didn't tell me how many primes there were, just that there were a finite number of them. So I'm going to get real creative here and call it here's the first prime, P1, here's the second prime, P2, so forth and so on, until I get to the nth prime. No idea what that is, but it's finite, so I can do that. The list ends. So now I have to think of a way to break it. What would it mean? Can I derive a contradiction here? What I would really like to do is I need to show if there's a list that contains all the prime numbers, can I show that that's somehow false? There's a prime not on this list. And I can get creative here. Let's make a new number, and it looks like the following. It takes all the primes, multiplies them together, and then adds 1. This is important because it means that P1 is not a factor, because you can't factor P1 out of here. Can't factor P2, you can't factor P3, so you can't factor out any of the prime numbers from this. So none of the prime numbers in this list divide R. Well, that's what makes a number a prime. So R would be a new prime number. But this contradicts that the list contained all of the different prime numbers. So we are forced to conclude there are an infinite number of prime numbers, because if we assume there's a finite number, we get a contradiction. One last example. If n is an integer and 3n plus 2 is even, then n is even. You have to be careful here with what happens when you're doing a contradiction, how the negation actually plays out. Remember, we're going to negate the entire statement to do a contradiction. So we're negating P implies Q. Well, that's equivalent to P and not Q. So we're going to suppose that 3n plus 2 is even and n is not even. Note, we've seen this proof before, but I'm just showing you that we can apply a different technique here. So we're going to make the assumption that 3n plus 2 is even and n is not even, and see if we can get a contradiction. So if n is not even, it's odd, so our assumptions will be 3n plus 2 is even, n is odd. By definition, if n is odd, that means there exists an integer where n can be rewritten as 2k plus 1, right? Our definition of odd number. It's important that we apply that definition of an odd number. That's what we know about odd and evens. So we can rewrite 3n plus 2 as 2 times an integer plus 1. So that leads to the conclusion 3n plus 2 is odd. Well, one of our premises was that 3n plus 2 is even. So if we start with the premise 3n plus 2 is even, and we conclude 3n plus 2 is odd, it's important that we can't go back and change things, right? We can't go back and fix it, as it were. This is a valid argument. So if we start with these assumptions, we end with these conclusions. It's unavoidable. So this is a contradiction. And since that's a contradiction, we've shown that if 3n plus 2 is even, you must conclude that n was even.